compared to this. I'm just not getting anywhere with this. It makes me wanna hide.
Aw, don't be embarrassed. Don't hide.
You should have seen mine the first time I tried. It took a lot of whoopsies to look this way.
No one's perfect on their first day. Whoopsie. Whoopsies, I made a mistake and it's okay.
It's okay. Whoopsies are what it takes to get better and better every day. Whoopsies, 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 whoopsies.
Well, what about this? I want to jump rope, but nope, I just can't do it.
Well, not yet. Come on and practice with me. You'll see there's nothing to it.
Whoa! Whoopsie.
Whoopsies, I made a mistake and it's okay. It's okay. Whoopsies, help me look, see, I'm better at this today.
Yeah! Whoopsie. Wait, was it yeah or woo?
I think it was woo.
Okay, say woo with us.
Woo!
There.
Alright guys, it's Taylor from Rootkit. Welcome to day 11 of Computer Internals. So first off, I just want to say thank you guys for showing up, coming out here in mass every single day. This has blown us away, the amount of participation that we've had. When we were originally planning this event, we were planning on just doing it and having these streams as videos afterwards. We plan on having no engagement, just talking to ourselves the entire time. So I appreciate you guys a ton for that. And if you guys watch us on YouTube, we're also live streaming on Twitch. We're dual broadcasting to both locations. If you're watching us on Twitch, we also have our YouTube, where we have a bunch of other helpful videos, like some basic tutorials that we can check out quick, and also just some entertaining content that we made over the course of time. So we have two categories that we make quite a lot of. I've been really enjoying YouTube Shorts and exploring these. He seems to get a pretty broad audience. We can cover some advanced topics in 60 seconds or less, and we're kind of liking that theme. Then we also just have our normal videos where we cover things like how AI can potentially kill video gaming, true video gaming, and then some more complex tutorials that need a little bit more than 60 seconds, or just some topics that we want to explore. Alright, so we're definitely getting close now to the end of Computer Internals. If we look at our courseware for the day, we'll be covering input and output devices and their architecture. We just have that, memory architecture, and then wireless and mobile technologies, and then we're finishing out our module here, and we get to networking and protocols. So yesterday, I promised you guys that we'd watch a little bit of NVIDIA flexing, showing off how cool their new AI is. Twitch gang, there you go. So we're gonna do that first. We're gonna watch NVIDIA just truly show us how far ahead of the game they are from everybody else.
Doctors can now sequence the human DNA in a couple of hours and predict the 3D structure of the DNA from the amino acid sequence. Researchers can use computers to generate new drug candidates, and inside a computer, test the new drug against the target disease. AI is learning biology and chemistry.
Hey, thank you, Driven
just as
Meds.
AI has learned
Thank you for the
images,
follow.
sounds, and language. Once in the realm of computers, fields like drug discovery will undergo the same revolution we're witnessing in other areas impacted by AI. None of these capabilities were remotely possible a decade ago. Accelerated computing at data center scale and combined with machine learning has sped up computing by 1,000,000x. Accelerated computing has enabled.
So there's some crazy numbers, 1,000,000 times more efficient. And then also, I just want to point something out to you guys. This man here, the founder of NVIDIA and the core creator, or initial, he's not here. He's not real. He's entirely himself AI created based off pictures of him, words that he says, how he talks, and then they gave it a script to generate this conference for us. And so this is just a huge flex by NVIDIA, just showing that they no longer even need real people to push their products. Their AI can do it. And I think that's just awesome that this is the age that we're getting into now. I think we've only ever seen it. Can you turn it up? Can you hear it? Volume is very low. And that's for the main video. That is very low. Okay. In the future, we'll rewatch a little bit of it. As he says some pretty cool stuff.
Can now sequence the human DNA in a couple of hours and predict the 3D structure of the DNA from the amino acid sequence. Researchers can use computers to generate new drug candidates, and inside a computer, test the new drug against the target disease. AI is learning biology and chemistry, just as AI has learned images, sounds, and language. Once in the realm of computers, fields like drug discovery will undergo the same revolution we're witnessing in other areas impacted by AI. None of these capabilities were remotely possible a decade ago. Accelerated computing at data center scale and combined with machine learning.
Yeah, advancements like this are making self-driving cars possible or even reasonable now. We don't need to have just huge computers, like those supercomputers that we checked out yesterday, running these AI algorithms or doing these computations for us. We're starting to be able to fit these in home computers and cars. So this technology of being able to learn, your car learning while it's driving is reasonable now. Tesla's doing it, and other manufacturers are doing it, like Ford. So I just want to show this off. And then before we get too into the weeds of things, we'll come back here and we'll do our shebang. I know you guys all know it by now, but for all the new people here, thank you for coming here, and thank you for everybody who's been following us on YouTube. There's a whole bunch of you guys yesterday. But we're going to talk about who we are. First of all, we're Rootkit, and we're bringing you guys 100 days of Rootkit. We're doing this for 100 days, starting on January 1st. We're on day 11 now. So why we're doing this? We've been working on this mission now for well over a year, trying to bring education to the whole world. We think that programming and other trade skills, like welding, shouldn't be for the select few that choose to teach it or go to college. We want to bring it down to everybody's level. Because there's tons of people that are just brilliant that just don't have access to college or even the internet right now. And so one way that we're doing that is we've been trying to create open source certifications on our GitHub and here on our website. And another way for engagement and to drive further development is by streaming and making videos out of our content. So that's why we're here today. You guys can support us financially on our website here by going to the How Do I Donate to the fundraiser. We can see here that we have a cool little tracker that shows at the top of the screen that you guys see. and it tracks it here. And we have some pretty cool goals here. Like we start out with story time from Elijah. Then we're going to teach for 24 hours straight. Then we get to shave Elijah's head, and then at 20,000 we shave his beard. All right, and then last thing to talk about on here is we have our blog where we have our giveaways, and we're running out of time, but our week 2 giveaway is coming to a close soon. I think we got 1 day left, so tomorrow will be the last stream of this giveaway. So come on over here and put your entries in. We're gonna be giving away some cool merch, which you can also purchase if you're not a lucky winner, or if you just want extra, or if you want to give it away to somebody. These are all limited time, so once the season ends, we'll be rotating these out with more. If you're interested in checking out our certifications, you can come over here to this tab. Give it a read through. All right. So over the last couple days, we've talked about what is input and output, and we defined it kind of at a very high level early on. The Driven Mads asks, do you plan on releasing videos of your 100 days of Rootkit? So yes, Driven Mads, we currently are just uploading the raw VODs on YouTube. We're probably going to push them to Twitch as well. I believe it's just a failure on my part. But we have, I think, 5 editors now that are chopping up the videos, doing different editing styles on them to make them flashy, make them fun, make them engaging. Then we're going to be pushing them out as a variety of different content of YouTube video architecture or shorts, or we'll play around with it. But all the content will be getting pushed out. You might see some repeat there depending on the style of how we do it. Okay, so yeah, so we talked about input and output and how we defined it at a high level because we're looking at how data can traverse our motherboard and go through those digital logic gates. So now we're going to dig in and we're going to get to what the nitty-gritty is of what input is and what output is in terms of computers and logic. Let's get into our book. All right, so input-output architecture. So input-output is just this I/O. You'll see it a lot throughout this book and a lot when you're doing research on this topic. It's just a nice shorthand for it, input-output. Architecture provides the mechanism for moving data around a computer system. So that's, once again, pretty broad. It just moves data. So a motherboard is the main printed circuit board in general purpose computers. So we talked about the 2 types of computers yesterday that we have our embedded and then our general purpose. So our embedded are made for like the Saturn V rocket. They're there just to do one task really, really well. They don't need to be reprogrammed and they don't need to be multi-use. These general purpose computers are kind of like what we have at home, our personal computers that we want to be able to do multiple things, watch YouTube, have Twitch open, and play Minecraft. Maybe open a calculator, do some taxes or something. So when you see here, this is our motherboard. You see it has this, pretty gross green PCB color that we looked up a little bit ago. And then we have all these lines on here. We're going to be getting more into what these lines are and how all of these different components here on the motherboard are connected. So it's the main printed circuit board in general purpose computers and other expandable systems. It holds and allows communication between many of the crucial electronic components of a system, so such as your graphics card, your monitors, your keyboard, your mice, your hard drives, everything that connects. This would be such as your CPU and memory and provides connectors for other peripherals. So does anybody have any questions on that first page? A nice little overview, getting us ready, getting us excited to get into this. What I did forget to mention, I was trying to set up some polling for our little check on knowledge that we do at the end of every stream. I don't think we're perfect yet, but we got something going for today. We'll see how it works. All right, I don't see any questions, so we're gonna keep cracking on. Okay, so now we're gonna start talking about what those lines are on the motherboard and how things communicate. Those things are called buses. And a bus is a connection between computer system components that moves data back and forth. So it's these lines here, and we saw them as silver lines on our motherboard. And all they're there for is not to look pretty, but to move data, those electrical currents back and forth. So figure 45 here shows how the bus connects the CPU, main memory, and input and output devices. And here you see here We have our CPU. And then we have this thing that we're going to get into later, which is called a north bridge and a south bridge. So the north bridge connects our main memory, and like a power goes in here. And our south bridge connects to all of our like not essential pieces of our computer. So these would be input and output devices, such as my headphones here. They get a lower priority than the CPU gets access to the resources it wants. Okay. So a bus is broken down into 3 lines. As we can see here, they all have 3 lines here. We have the address line, the data, and the control line. Then we can see here that one of them is a one-way and 2 of them are bidirectional. So our address line indicates location data should be read from or written to. So we can see here the CPU writes data out to other devices. So that's what that's indicating. Then we have our data line, which transfers data. Then we have our control line, which carries command and status signals, such as read-write commands, interrupts, and synchronization. We'll delve a little bit more into what those mean in a little bit. So we learned about our types of CPU, that we have our RISC and CISC, and then there's this type called ARM, which is more found in like our small devices, such as Raspberry Pis and our phones. And they use a concept of a system on a chip, or SoC, which is a processor, memory, and bus on the same chip. Most mobile phones utilize this in their ARM-based SoCs. Below is an ARM bus architecture, an example of a SoC. So we can see here, like on this Raspberry Pi, that there's nothing connected here. There's no graphics card hanging out. It's all on this one board here. And they do that so they can make them super efficient, but also they can put a nice case on it. You know, you don't want something protruding out the side of your phone. So by having it all there, soldered on and nice and sturdy, it stays on there. So we can see here that they have everything connected. So they'll have things like USB hubs, which connect all the extra devices that you want to plug into it. So like if I put a keyboard into the Raspberry Pi. Then we have our CPU memory, which has access to all of its onboard chips as well. So it has the audio out, an SD card, which is exactly what the Raspberry Pi uses, just a small little SD card at the top here. Then we have some video output and HDMI. So below is an advertising slide from Apple. It's in regards to their new M1 chip. This was written a little bit ago. I know the M1 chip's not like the newest kid on the block anymore, but it's still kind of new in technology speak. So it's an ARM-based processor using a SoC design for their laptops. So this is kind of cool because even most laptops, like mine over here, it has separate subcomponents, but they're not all integrated. Hey, thank you, Toothmax. Thanks for the follow. And so, you know, Apple's able to make their laptop extremely small, extremely light, and extremely powerful for what they put into it. And so we can see here that they divided theirs up in an interesting way where they have 4 high-performance cores, so these top ones. Then we have 4 high-efficiency cores. These are more energy efficient for longer-lasting battery. And your top ones are for like big burst loads. So they have these subdivided. And then they have the 60-core neural engine, which is just doing some machine learning and accelerators, and it's 8 cores for their GPU, which they have here. So this is their graphics card that's integrated into the same chip as their processor. So that allows that communication to happen extremely fast and be extremely efficient. They don't have to exert a lot of energy to do that transfer. They have some other subcomponents in here that we're not too worried about today. So the x86, which we learned about, we looked into a little bit about how their assembly instructions work and how they're pretty efficient and pretty simple compared to 64-bit, which is huge base instructions compared to x86 32-bit. So x86 bus architecture separates the memory from the rest of the input-output with 2 bridges, the north bridge and a south bridge. Our north bridge is used for memory and our south bridge is used for input and output devices. So we can see here that we have our CPU, which is our central processing unit. That's the king. That's the thing that does all the work here. So it has direct access to its DVI and its memory. We can dig into what a DVI is. So DVI is Digital Visual Interface, and it's this old looking connector that I'm sure we've seen floating around. Some people still use it. There's nothing bad with it, but when you're building a new computer and you just set one up, you need some way of interfacing with it even before you get anything working on it. And so this is always there. This will work for you even before you have an operating system. Sometimes if you have like a graphics card plugged into your new computer that you're setting up and you're connecting through that, it just won't let you in because you haven't told the computer how to use your graphics card yet. These are good to have around if you're building computers or fixing computers. And they're still pretty competitive in terms of how much data they can push through. I don't remember exactly. Yeah, so it used for the mandatory low pixel format display mode of VGA, 60 Hz. So it's not bleeding edge, you know, it's not 4K HD, but it's not horrible. So we can see the CPU has access to everything it needs. So when it sets up, it just has to go here. There's really short lanes that are close together physically on the motherboard, and also they're streamlined so they go really, really fast. They don't have to go through any stages. Then we have this south bridge, which handles everything else. We have this I/O bus, which we'll get into later what an I/O bus is, but it's basically just a highway for everything to connect to. We see that we have like our hard drives and stuff like that way over here. They connect to the I/O bus and go through the south bridge, as well as our keyboard, our monitors, our mice, our headphones, any smart card readers that you put in here. How's everybody doing so far on this topic? All right. Oh, I did want to remind you guys that we do also have a Discord where we have a bunch of champions, which are people who have contributed to the community in some way, or they're here voluntarily from a company partner. They can donate experts to us as well, and they're called champions. And our Discord is full of those champions, but also other like-minded programmers that are learning technologies out there with you guys and us. And we're all there to help each other grow. And also that's where I'm reading from for the stream, so it's a great place to be. We play games there. We stream everything there as well. All right. So the above illustrates a model input-output configuration. The bridge allows communication between dissimilar buses. Since buses communicate in different languages and at different speeds, the bridge functions as a translator. So that's an interesting thing. If I'm a manufacturer of a hard drive, and then my brother is a manufacturer of mice, who says that we have to use the same language behind the scenes to communicate to the CPU? Well, nobody, because we can all implement it differently. And so that's what these bridges do, is they do a little bit of the communication here, where the south bridge goes, okay, what's talking to me, the keyboard? It interprets and translates what it's trying to say, and translates that to a common language for our processor to handle. And it does that for all these devices, which takes a lot of the load off our CPU. So input-output modules interface between the processor, memory, and one or more peripheral devices. So you can also have hubs, like USB hubs, which connect multiple devices, but for our reasons, it's all the same. It's just connecting out to devices. Similar to a CPU, however, they only have one purpose and may include their own memory. So a lot of devices, like modern day keyboards and stuff like that, contain their own memory as well to do some logic to allow you to, I don't know, make your keyboard have pretty colors, or to let you set macros up so when you hit a button it opens Notepad and types hello, or cool things like that. Those are on your devices. And a device interface is a physical connector attaching peripheral devices to the computer, also referred to as ports. So the ports are on your computer. Take a look at the back of a computer. So if you're on a desktop computer, you can see stuff like this where they have these big ports on the back. And so these are called ports because they're the receiving end. They're what we plug into. And then we have our device interface, which is the other side of that. So like that's the USB part that you stick in with a flash drive. Okay. Oh, I did miss a sentence. Let's go back. So a device interface is a physical connector attaching peripheral devices to the computer, which is also referred to as ports. A device interface consists of at least 3 lines, which we talked about earlier, the control, data, and status, and it still has to have those same 3. And a device interface has the same name as the bus to which it's connecting. That's an interesting detail, that it has to be that way to know how to communicate. And so these aren't the same names as the lines on a bus, but they still follow the same methodology as that. Now we're going to be getting into bus topology. So let's look up the word topology first, because I think that's a weird word. So what is topology? So topology is the way in which it constitutes parts are interrelated or arranged. So basically how things are laid out, how they look. Okay. So bus topology is the arrangement of the connections between computer systems, or computer system components. There are 2 main topologies used to connect components. We have our multi-point bus, and we have our point-to-point bus. So let's get into what each one of these does, and why they're different and how they're similar. So a multi-point bus connects more than 2 components together. Since there is a common pathway, a control line is needed. So we have this common path here where they all split off of that. Then we have our control lines. Control is accomplished by using a master-slave or assigned priorities. Now, that terminology has been around for a long time. Oh god. Master-slave has been around in textbooks for a very long time. It's used in mathematical terms, it's used in engineering, and it was also used in computer engineering. But our culture as it is nowadays has been trying to get away from the master-slave terms. So if you're reading old documentation, you may still see master-slave, but nowadays we're calling it a parent-child, which is much more indicative as it is anyways, because children don't have to listen. Children can go rogue all the time. You say that, you're not allowed to talk on network, and the device just starts spewing things on the network. It doesn't have to listen, you're just telling it to. That's what the sense is about. So our point-to-point bus connects only 2 components together. So for example, our RAM to our north bridge, where it's that one-to-one connection, the north bridge to memory. It's really, really fast. They don't have to ask to communicate, they just communicate. There's nothing in between, like an arburator that has to say they're allowed to talk, or a control line where they have to ask for permission to talk, or have like a parent-child architecture. That makes sense so far? All right, looking good. I keep moving on. Okay. So now we're getting on to how we handle these things on the bus with the different topologies. We're getting to bus arboration. Is a system for resolving bus control conflicts by assigning priorities to bus control requests in a multi-point bus topology where there is more than one connected device. So what we're saying is, back up a little bit, if all 3 of these devices here try and communicate at the same time on the same bus, they're going to block each other out. The CPU won't know what to do, it's going to get overwhelmed. So there needs to be a way of deconflicting who can talk and how, and for how long, and how much data. That's what we're talking about here with arboration. So what this does is it assigns priorities to each of these devices and says that, the one with the highest priority can talk first, or the one with the lowest priority talks first, or, whatever gets this amount of time. And that's implemented in different ways. But the idea is to implement priorities into them. So you can say certain devices are more important than others. So one way of implementing this is daisy chaining. Devices are connected in a series, so one after another. The requesting device closest to the arburator gets the bus first. So device 0 is closer to the arburator, so it gets to talk first. And then when it's done, it passes the bus access to the next closest device. So device 1 then gets to talk. And this continues until there are no more devices. Device 3 passes it all the way back to device 0. And by the way, I'm pretty sure Elijah covered this, but the reason it's called device 0, not device 1 to start out with, is because in software development and computer science, we start with 0 as our first number. You're going to see it a ton. I know it's a little weird, but it's just a thing to remember. So we always index off of 0. Well, so this kind of makes sense, right? So The person with the highest priority or closest to the operator gets the microphone, they say what they need to, and then they hand it off to the next person in line. And it goes all the way around and keeps going around forever. This has obviously some drawbacks. Let's say like device 0 needs to talk a bunch, device 1 needs to talk a little bit, and device 2 and device 3 don't care. Well, it still has to get passed around every time until it gets all the way around for device 0 to say everything that it needs to. Or if they're all talking a lot, it's going to take a while to get all the way back to device 0. So each individual task will take a long time because it keeps getting stopped at each roadblock. So centralized parallel. Requests for bus access are sent via direct control lines, so they each get their own way of communicating with the arbiter, not just one line passing it back and forth. And it goes to each device to a centralized arbiter. The arbiter compares device priorities and provides a bus grant on the appropriate device control line. So if device 2 here doesn't need it and they have a low priority, but device needs it and has a really high priority, it's going to keep passing it back to that more and more and more. And it can do some cool math with it where it says like 90% of the time is device 1, and then we'll share the other 10% of the time between device 2 and device 0. However, it needs to break that up. And a lot of operating systems like Windows kind of have these like algorithms built in behind the scenes where they monitor processes and how your CPU is utilizing its cores, and it will start to prioritize and assign it slightly better to be more and more optimized the longer you use your computer. So distributed using self-selection. All devices communicate bus requests to each other. The device with the highest priority is granted access to the bus. Priority is determined by the device code in the bus access request. So this is a little similar to this one, but instead of having that similar person, it's more of like a socialist environment where they all push out their tickets, they read each other's, and then they make a decision based off that. So they have to be all in agreement. I haven't seen this one used too terribly much. Actually, what we can do is go look up some examples. Do we see anything here? There are a lot of people talking about it. But then they don't. They don't even talk about it, do they? Like a rotating priority method. Here we go. So advantages. This method does not favor any particular device and processor. Ooh. Hey. Thank you for the follow. We're starting to grow our family over here. This method is also quite simple. So it just keeps going around and around and around, passing it out. This is a rotating design. So it's similar to the one that we're looking up, but you can see that it goes through each of them. So that's like our first one. And disadvantage of this one is it's adding bus masters is difficult as it increases the number of address lines of the circuit. And if one device fails, then the entire system will not stop, or will. If one device fails, then the entire system will not stop working. That's interesting. All right. Then we have bus protocols. So the bus protocol is a method that computer components use to transmit data between the sender and the receiver components. So serial communication, see that word again, serial, which means it just happens in serial, so in a sequence, one by one, sends data one bit at a time. Serial communication relies on handshaking for synchronization or asynchronization. Basically, they have to agree upon each other. They have to meet in the middle and have that handshake and agree who's going to send data first, and then communicate back and forth. So we have parallel communication, which sends a group of bits via multiple data lines. Parallel communication relies on a clock signal for synchronization. While parallel communication is faster, it is only suitable for short distances. Crosstalk between data lines and delays caused by clock skew make parallel buses costly. So here we can see that the output just shoots all of these out at once right to the input, and it's the input's job to try and figure out the order they're coming in, how to put them back together to make sense of it. That's why it's saying here that the clock skew, if the clock has some issues in it, it may become unusable or unreadable, and you may lose data. So handshaking is a series of steps to coordinate asynchronous communication in which sender and receiver proceed to the next step only when both parties agree that the current step is complete. The series of steps are: Step 1, bus control is active and data memory address is put on the address line. Basically here we have to say that we have a way of communicating, we have that lane open for us, and also we've put our address there. We're able to talk to each other. We know each other's locations, or their phone number basically. Step 2, memory system puts required data on the data line. So you actually have to transmit that data, which is energy going onto that line. And step 3 is data is acknowledged via the control line. The device 2 says, hey, I got your signal, and sends that over the second line back to the original device sending the signal. And this is how we guarantee communication. Because if a device sends something but never gets this acknowledged back, it knows step 2 or step 1 had an issue. We're also going to see that come up later in networking because it's a really good system. We do it all the time in real life where I say or I tell you something and I'm waiting for you to agree with me or say you understand or you don't understand or ask for help. So we kind of do that in English passively. So input-output device in buses. Common types of input-output interfaces / buses used by computers are a serial port or an RS-232, which is a point-to-point serial communication. So this is just basically a way of passing data. You'll see these a lot used for point-of-sale devices at like a gas station, where they have that place where you can put their credit card in. Well, that usually connects via serial port to that computer there, because they're not interested in like sending too much complicated data. It's just raw data that they want fast. We then have our parallel port, which IEEE 1284 defines what this is and how it has to be, which is another point-to-point parallel communications. So this is serial, this is parallel, pretty similar functionality except more data throughput on this. We then have some small computer system interfaces, or SCSI, which is a multiple point parallel bus with devices daisy-chained together, commonly used commercially for hard disk drives and tape drives. Yeah, so basically you can see these SCSIs on like in servers. So these hard drives are on these like little caddies here, and they can just slide in to their slot. And so it'll just be like a receiving port with 8 open slots for these to go into. Yeah, so here we can see, not excellent, but we can see these are all hard drives that are just stacked up. So in the back here is just a port to receive that hard drive, and those are normally with that SCSI that they communicate over. And then the SCSI doesn't do anything super intelligent by itself. They normally have to have a controller behind the scenes which handles those connections and how to read and write from them, which ones are filled, unlike when you connect it just via like SATA. We then have our serial attached SCSI, or SAS, which is a point-to-point serial bus built on the SCSI standard. It is now compatible with SATA devices, provides higher throughput and hot swap capabilities. So this is pretty cool, the ability to be able to pull out a hard drive and just put a new one in if you were running like RAID, which so RAID is basically a way of having redundant array of independent disks. So these independent disks are these hard drives. So basically we say that we want it to be redundant, which means that it can fail, one hard drive can fail and you don't lose all your data. And then we want an array, which means just a collection of hard drives. So with RAID, we can put a bunch of hard drives together and make a group of hard drives that allow failure so then you can hot swap them out. This is really important when you're working for like a company or a company is running and they have servers with customer data or information that, is costly. They want, it's money to them. They don't want this stuff disappearing, so they'll put this in a higher RAID to allow for more failures. These SATA SAS devices are what you're going to see on your personal computers at home. This is what's going to probably connect into the back of your hard drive and connect to your motherboard. That way you can add more and more storage because it keeps growing. All right, now we're getting some older ones, so you're not going to be seeing too much anymore. But we have Parallel Advanced Technology Attachment, or PATA. Multiple Point Parallel Bus, aka an Integrated Drive Electronic, or an IDE. It was used in older computers to connect hard/floppy disks and optical drives to the motherboard. So you can see here it has this ribbon tape, which we used to see a lot in older computers. We don't do that anymore. So you're not going to be seeing this, hopefully, too much. We then have our Serial Advanced Technology Attachment, or SATA, which we saw a little bit earlier. This is the PATA successor, so instead of having this long ribbon, we just have this little wire here. And this allows for hot swap, which we talked about, and it works for most types of mass storage devices, such as hard drives, solid-state drives, and optical drives. And the good thing about these is this actually supports the speed now that our new hard drives and optical drives, or SSDs, are communicating over. Because a lot of these older connections just can't support that speed. We have our Peripheral Component Interconnect, which is an express connection basically. So PCI or PCIe, depending on if it's express. And an expansion bus that uses channeled point-to-point serial communications. It's found on both ends of the north bridge for graphics cards and south bridge for sound and other I/O cards. So this is a little bit older of a motherboard now. When we see here that we have our CPU right here, and then we have our PCIe, which is for the big slots, is the bottom point of a graphics card. Nice little typo there. Yeah, it's for this bottom part here of these hard drives. Those slot right in here, and they usually face this direction, so they're right out the back. We have our RAM here, which is that memory that communicates directly with the CPU, so we want that really, really close. The CPU wants to be able to handle it whenever it wants. And then we have our other smaller devices that can go into here, our PCIe, we have our PCIe here, and then our little mini PCIe. You can see kind of like the order of importance, right? So the RAM is located really close to the central hub, the brain. Then we have our graphics card here because it wants to be able to put a lot of throughput out through this, so that's closer. And then it gets down to least importance. Okay, and then we get to our Universal Serial Bus, or USB, which we've all seen, these little USBs floating around. So USB is a point-to-point serial bus that connects many types of peripherals, from drives to phones to cameras. Connectors include standard, mini, and micro, and they keep coming out with a lot of these. We're currently on like the Type-C's, everything's going to now. I think Apple just got forced to go to this. But I'm sure everybody's seen Type-A. My headphones connect to the Type-A. I have a USB thumb drive over here. So there's many different things to implement this. Let's go take a look at a USB thumb drive. Let's just call these USBs, but the USB is the actual connector part here, and then just has a stick of memory on the end of it, which I'm sure everybody's used by now. And we can see, even though they're changing what the port looks like and what that actual interface looks like, it's still relatively the same. It has higher throughput the more generations we go up. So these new Type-Cs, they do 20 gigabits a second, which is crazy compared to we were looking at megabits a second just a few years ago. And your computer probably even comes with USB 2.0s on it. Those ones on the front of your computer, closest to you, are probably USB 2.0 or maybe USB 3.0. We then have Video Graphics Array, or VGA, which is a standard analog video interface for color resolution, 640 by 4080. I'm sure most people use a little bit higher resolution now, and computer monitors. This interface was so widely accepted that it is the default interface for compatibility. Almost every motherboard you get will have this on it, unless it's a highly specialized one. And like it says, it's just the default. All my servers behind me and all my computers here all have a VGA. So I have a monitor with a VGA port on it, and I have a bunch of spare VGA cables because I know that they're always going to be used. They're great for checking if other ports have failed. We then have our Digital Video Interface, or DVI. Video interface designed for digital-to-digital connections, provides for VGA compatibility with pins in for analog data. So it looks extremely similar to DVI or to VGA, but just has this extra little bit. Now we're getting towards more what we're all probably using. We have high definition multimedia interface, or HDMI. This is what we see on the back of our TVs, our monitors, and pretty much everything now. They're a high resolution multimedia video and audio interface that includes digital rights management for copy protection, which most modern displays and televisions use HDMI. So this is really cool because it has video and audio over one cable. Because if you connect any of these guys up here, you also need to run another cable to get your audio, which you'd see like those 3 like old audio cables. Cables. So we have aux, we have coax, and then I don't remember what the old ones. They are RCA. Here we go. So RCA cables, which you'd see like coming out of your surround sound and stuff like that, going to your TV. HDMI could just do this across the same wire, which is really nice. For one, looking pretty cable management, you have to run one cable down the center of your TV to hide it versus having 6 cables coming down. But also, it just allows more technological growth because you only have to iterate on one thing. So DisplayPort, or DP, digital display interface for connecting a video source to a display device. It can also carry audio, USB, and other data. This is the first display interface to use packetized data, which we'll get into more with networking and protocols, what that actually means, and why that's such an advantage. But basically, all the other ones just stream data. They're just sending things through the wire, because there's only one-to-one, so they're just sending it. This here actually does some logic, and these are basically like letters. Like, so when you're doing mail, you put it inside an envelope. A packet is basically an envelope which contains your information inside of it, but also contains an address and other data on how to get to where it wants to go, and what's inside. So now we have Thunderbolt. Thunderbolt is the brand name of a hardware interface developed by Intel. It was in collaboration with Apple, and it was supposed to be like the USB killer. This allows the connection of external peripherals to a computer. Thunderbolt 1 and 2 use the same connector as a mini DisplayPort, MDP, whereas Thunderbolt 3 reuses the USB-C connector from USB. I don't think these have ever really taken off, and I'm pretty sure they're falling out of existence, but we can see how popular they are. We can see here is an article, January 2020. Thunderbolt 4 arrives in 2020, but USB will remain the king. And it looks like Thunderbolt 4 just came out, which is pretty cool. Like, I didn't even read up on this, so I'll have to read that. But yeah, this is basically the same thing as USB-C, but through Intel and Apple. Alright, so we're on our final chapter for the book for the night. Alright, so we're on input-output control methods. So copy protection, like copyright. So no decisions. So copy protection is, well, here, we can actually look it up. So we can see here, this had a nice little blur about it. So we have High Bandwidth Digital Content Protection, HDCP, is a copy protection scheme to eliminate the possibility of capturing digital content from the source to the display. So it is designed to protect digital signals when using a digital video interface, DVI, and high definition multimedia interface, HDMI. So it wasn't super great, but yeah, it's for security basically. It allows a device to say when it's being, watched and not watched, but also allows the receiving end to say when it wants it and when it doesn't want it. It's developed by Intel to prevent copying of digital audio and video content as it travels across connections. So yeah, I believe it also does some like basic encoding where, so if you put a tap in the middle and you start listening on it, meant to stop HDCP encrypted content from being played on. Okay, so here we go. The system is meant to stop HDCP encrypted content from being played on unauthorized devices. So yeah, so basically if we put a tap in the middle and we want to snoop on it, and try and get access to what's going on through that line, it has a little bit of protection baked in here with encrypted content, which would stop me as a third party from, just stealing your TV or whatever, or just jacking your data that you're sending. So that's pretty important. It's not that massive of a problem, but it's a problem, and we have a solution, and it doesn't detract from anything, so that's pretty awesome. As long as you're using modern display ports. Okay, so talking about our control methods, we have the computer system's I/O modules use control methods to communicate with the CPU. Instructions are passed using memory-mapped input-output, and data is passed using either programmed, interrupt-driven, or direct memory access, which we'll dig into a little bit, but programmed is exactly what it says. It's been told how to handle that data being passed. We have interrupt-driven, which an interrupt is an event typically triggered by an input-output device, which interrupts are asynchronous events since they occur at random times during program execution. And so basically it is exactly what the word is. It's an interrupt. It says, stop, I'm done. So when you get to the end of a file, there's an interrupt there which says, stop reading, don't go any further, you've reached the end of this file. Or direct memory access, which is just that, it's just direct, it's pulling straight from it. So this will be for streams like audio and video. We then have our memory map, or we're going to delve into our memory mapped input-output, is an I/O scheme in which portions of RAM are assigned to input-output devices, and reads and writes to those addresses are interpreted as commands to the input-output devices. It is commonly used for device driver communication to a device in the form of instructions. So this is basically using a section of the RAM, which it gives to each one of these devices, a common place for our computer to write to tell it to do something. So it can then have some like scheduling that happens, or like a queue of things to do. We then have programmed input-output, or polling. It's a process of periodically checking the input-output device status to determine a need to service the device. So yeah, this is where it's the input-output device. We're checking to see if the hard drive is busy. If it's not busy, we'll give it a new task. If it is busy, we'll wait to give it a task. So that's that polling action happening. Programmed input-output works well with slow devices, such as keyboards, mouse, since the computer may not be checking the device for new data when it arrives. Yeah, so this is a big thing. Whenever you hit a key on your keyboard or you click your mouse, you just expect it to work, and so does the device. But your computer has to be sitting there waiting for that to happen. So programmed I/O has the most overhead of all the input-output control methods. The CPU must save machine state, check the status bit of each device, and service any requests, then restore machine state. So the status bit is like where it was saying like it's ready, it's not ready. So it's a little bit of polling happening there, but it's done on a bit. And then it has to service a request and then set that bit back to being available. So CPUs test the device's status before transferring each data byte, so the CPU is unable to service other processes until that device is done. It provides data rates that are a bit slower, but reasonable for the speed of the device or the human using the device. Yeah, so once again, like our keyboard and our mice, they process way faster than our brains can register. It doesn't have to be 6 gigs a second like our, SSD. So we don't necessarily care about the speed as much of our keyboard as we do other things. We then have interrupt-driven input-output. It's divided into two categories: interrupts and exceptions. Interrupts and exceptions are used to interrupt normal operations of a program executing on the processor when a problem occurs. So the CPU is doing a task, it's counting to 100, and then you do something where your keyboard sends an interrupt to the CPU and says, stop what you're doing, drop everything, you gotta come handle me now. An exception is an event resulting from the execution of an instruction of the current program and is therefore a synchronous event. There are three classes of exceptions: traps, faults, and aborts. So what this is saying is your CPU is doing a thing, it's counting to 100, it gets to 22 and it just can't figure out to count to 23 for some reason. Something goes wrong in it, it has an exception. Or let's say we're doing a divide by 0, that's going to raise an exception. So let's look at our three different types of exceptions. We have traps, which is software invoked exceptions. A programmer using a try except block to raise an exception intentionally. So let's say that I'm writing a program and I want to take some input in from you. I want to take your name and you give me blank input. I can have this try except block set up to say that if I get blank, just fail successfully. So I want you to say that it failed, but I want to do it in a clean state. I don't want the CPU to like panic. I just want to close everything down. So this would be an exception that I'd raise to have my program fail successfully. All right, so we're moving on to faults. Faults occur when attempting division by 0 or when accessing memory incorrectly, a page fault. So this happens, like it says, dividing by 0. If you do it on your calculator, it doesn't know what to do. It can't. Also, you probably can't off the top of your head, because I don't think anybody knows how to do that. But also, let's say your computer goes and it tries to pull something out of memory. It says, I want something out of memory slot 3 of 10 bajillion. And it's not allowed to read from there, or it's not allowed to write from there. It's going to give it a fault saying page fault. You're not allowed to do that. Or you can't do that. Then our last one is aborts. Used to report severe errors, such as hardware errors and inconsistent or illegal values in the system table. So these are important for, let's say that we're writing to a drive, like a CD. We're burning a new CD, and all of a sudden the CD drive fails. It's going to raise an abort, which tells us, like, hey, something failed over there. Just stop sending data. Stop what you're doing. So you can see here it interrupt saves variables and registers, look up the ISR address in interrupted vector table. So this isn't too important, but we're just going to follow the flow here of like how an interrupt stops the CPU. So it does a nice little lookup. It places the ISR address in the PC. A service interrupt restores saved registers and variables and branch to save PC. So basically an interrupt allows us to save these clean states where you can interrupt it, but it's going to take a little screenshot of what it was doing. It's going to handle your thing, and it's going to come back and continue on with what it was doing. It's not going to like restart back at 0, because it may not be able to. So interrupts and exceptions are handled using an interrupt descriptor table, or an IDT, and interrupt service routines, ISR. An IDT is a data structure used by an x86 architecture to implement an interrupt vector table. The IDT is used by the processor to determine the correct response to interrupts and exceptions. So it's kind of a lookup. You have a list of like, hey, here's the things you can handle, and here's what to do with them, or how to handle it. An ISR is a procedure executed to fix the error. So the IDT contains all that list, and the ISR is on that one side, which says like, okay, if this happens, if somebody kicks in your door, you respond by shouting at them. That'd be an interrupt. Interrupts and exceptions are vectored events. Each interrupt, so once again, vector just means like a collection. Look up. What is a vector? So a vector is an object that has both a magnitude and a direction in math, meaning it just has like 2 fields to it. It has 2 independent properties. So left and a right side of that table. It's divided in the middle and you have 2 sets. So interrupts and exceptions are vectored events. Each interrupt and exception has a number that is used to index a vector holding the address of the appropriate ISR. So it has what the error is and how to handle it. A one-to-one relationship. And how it deals with that particular problem. The CPU handles interrupts and exceptions in 2 ways, maskable or non-maskable. All interrupt requests, or IRQs, and exceptions that may be ignored by the CPU are maskable. So if the CPU has the choice of like your keyboard interrupts that you can do, like Control-C, your CPU can choose to ignore that. So that means it's maskable. And if it can't be ignored, then it would be non-maskable. So hardware and software failures that may not and cannot be ignored by the CPU are non-maskable. So direct memory access, or DMA, is a mechanism that provides a device controller with the ability to transfer data directly to or from memory without involving the processor. So that's pretty cool. If you can cut out the big brain in operations, just do your own thing on the side, you don't have to bog it down with what you want to do, and it doesn't have to get bogged down by handling your problem. So for devices that transfer large amounts of data, disk controllers, it is wasteful to tie up the CPU transfer data 1 byte at a time. Devices that utilize DMA possess a DMA controller. This is where I was saying, like those hard drives that are hooked up to the back of that bay, there may be 8 of them in each one of those bays, and they have to have a controller behind it telling it how to communicate with those hard drives. It doesn't make sense for every time that controller wants to communicate with a hard drive to first go back to the CPU, say, how do I communicate with it? Can I communicate with it? It just does it, and it's always waiting for the CPU to give instructions. So DMA has very low latency, lower than others because it doesn't have to go through the CPU. And DMA has the fastest transfer rates because it can have a lot of parallelism and it doesn't have to go through the CPU bus. But it has, at the cost of additional hardware complexity, you have to have that extra physical piece of hardware, that chip or something like that controller on your motherboard. So here we can kind of see how it goes. We're not going to dig into this, it's kind of convoluted. But basically what it's saying is the DMA can do all of these things on its own without coming back to the CPU. The CPU could be doing a lot of other things while you're writing to the drive. And then it just says, hey CPU, I'm done. And it transfers whatever the CPU needs. Alright, so that concludes our book for the day. And we're now going to get into our check on knowledge. But instead of that, we're going to try doing that through a interactive quiz on our stream. So let's see how this works. Now, I don't know if this works on YouTube and Twitch or if it's just going to be Twitch, but it's through the Twitch plugin, so kind of likely. Start the game. Check on knowledge of military. So yeah, it is very military wording on it. Ooh, so there we go. Okay, that's kind of pretty. We got a nice little pop-up there. And sorry for the fact that I couldn't have true or false. I need to manipulate this a little bit more. Nobody clicked it. Alright, so we'll go through it together then. We'll keep working on that. Alright, so our first question. Match the term to the definition. Have the see, is that up on the screen now? One second while I try figuring out this WizKit. Alright. How is it going? Still there. Things seems to be hanging around for a while. Okay, looks like I might just be stuck on the screen till the end of the stream. We'll just verbally go over these. It even blurs it out. That's okay. So it's not doing it on YouTube, which is awesome. Which is messed up, it looks like. But it looks like if you refresh, it's gone. Okay, cool. Okay, so master term to the definition. Sends data 1 bit at a time. We have a whole host of choices here. We have sends a group of bits via multiple data lines. So we have multiple data lines. And then a method that computer components use to transmit data between the sender and the receiver, and a series of steps to coordinate asynchronous communication in which sender and receiver proceed to the next step only when both parties have agreed that the current step is complete. Anybody want to take any stabs at these? So because we have data being sent 1 bit at a time, so it's in serial, we're going to choose serial communication for that. Then it sends a group of bits via multiple data lines, so we have multiple things going on here. So we kind of like that. We're going to choose multiple communication. A method that components use to transmit data between the sender and the receiver. Line is referring to bus protocol. On to our next question. So, true or false? A bridge is used to allow communications between similar buses. So here we have multiple like input-output devices. They're all speaking to like the south bridge, which acts as a communicator. So for this, I think we're going to do true, but it also allows communication between dissimilar buses. Match the terms of definition. Used to report severe errors such as hardware errors and inconsistent or illegal values of system tables. These are things that it cannot come back from. Or we have our software invoked exception, which is something else doing on a keyboard and mouse, which would be a trap. And then we have divided by 0 fault. Leave those away. Match the term to definition. Connects only 2 computers together or connects more than 2 computers together. We have multi-point bus, single point bus, and point-to-point bus. 2 components together. More than 2 components. I say computers, I meant components. My apologies. Didn't learn how to read. So it connects only 2, so we have our point-to-point here. And it connects more than 2 components, so it has to be a multi-point bus. False support. Oh, I messed up on this one. Here's what we can do. We can go back to our book. We can look it up. We can come down here. We can look at our interface. The control methods. Here we go. So a trap is a software invoked exception. That messes up. The trap is a software invoked exception, so we got that one. We then have our faults, which occurs when attempting a division by 0 when accessing memory incorrectly. Oh, okay. Gotcha, decisions. Yep, so these are looking like they're all right. Which is unique. So system on chip, or SOCs, are only able to be done with RISC-based computers. Are these only able to be done with like our ARM-based reduced instruction set, or can they be done for more complex? False for the bridge question, only going between similar components. Did it say only going between similar? It doesn't say only, it says a bridge is used to allow communications between similar. But I do think this is actually false, because I think it's what it's getting at is dissimilar buses. So like multiple different types of input-output devices. But might be overthinking it. We'll see. System on chips are only able to be done with RISC-based processors. That is false. Select all of the common types of I/O interface buses used by computers. Oh, wow. I think they all are. We covered SATA, we covered PCIe and PCI, we covered SCSI, mouthful, which are those hard drives connected. We covered USB, Universal Serial Bus, and DVI, which is a default display. And input-output is short for, I/O is short for input-output. I've said that one about 1,000,000 times so far tonight. A bus is not responsible for connecting all computer system components together and moving their data. An interesting worded one. The bus itself is not responsible for anything because it's just an interconnected electricity current. We'll see on that one. An event typically triggered by an input-output device. Programmed I/O, memory mapped I/O, exception, interrupt, or direct memory accessed. A mechanism that provides a device controller with the ability to transfer data directly to or from memory without involving the processor. This is the direct memory access, the DMA. An input-output scheme in which portions of RAM are assigned to I/O devices. So we have the portion of it being mapped to memory. Is an event resulting from the execution of an instruction of the current program and is therefore a synchronous event. So these are the exceptions that can be brought up in a program. The process, oh, I see, an event typically triggered by input-output device, we'll come back to this, do an interrupt. Then a process of periodically checking I/O devices to device status to determine a need to service that device. So using our last one, we have our program to put output. To be classified as a system on a chip, or a SOC, a chip will need to include a processor, memory, and a bus. That's kind of interesting because that doesn't include it having its graphics processing unit, so a way for displaying anything, or any input-output. It just says that it needs its processor, its memory, and a way of communicating with that memory. So I think this is false. We'll see how I did. Probably not the best. All right, we got an 88% tonight. Yeah, so here it is a true. That it does, in order to be classified as a system chip, that's all it does need. Interesting. Yo. That's right, it just needs a 3. You got that one right, decisions. Ooh, then I selected the wrong one for this. Sends a group of bits via multiple data lines. That was supposed to be parallel communication. I chose multi-communication. All right. So that's where we're going to be ending our stream for the night tonight. So if you guys have any questions, fire away in chat. We'll cover them in chat tonight, and then we'll cover them in the stream tomorrow as well. Thank you guys for your participation. Have a wonderful evening.